This lecture is recorded for first year IT students of A.D. Patel Institute of Technology, New Vallabh Vidyanagar, for the subject of Basic Electronics. So friends, in the last lectures in the offline mode in Chalk and Talk, we have covered for the fixed bias circuit. So we have seen the fixed bias circuit. So it is the basic biasing circuit which utilize only one battery, where there are two resistors which are RB and RC are connected with the transistor. Then we have analyzed the circuit. So we have written the loop equations in the input side, where the input side loop contains battery, resistor RB and the drop VB. So we have written the equation, we have found out IB. From the IB we will get IC is equals to almost equals to beta IB. So one of the parameter of the Q point is IC, so that we can find from the input side loop equation IB and then IC. Then on the output side, if we write the loop equation, so by writing the output side loop equation, we will have VCC is equals to ICRC plus VCE. So what we will get is VCE from that equation. So after getting the VCE, okay, we will get the another parameter of the Q point, and then we can find Q point, and then we can locate it wherever we want to set by using these equations. After that, we have seen the numerical in the class. After that, I have to discuss this point, why fixed bias is not used. So friends, we have discussed earlier thermal runaway. So the point is, fixed bias cannot stop the thermal runaway. So what was the thermal runaway? Let me show you with this diagram. Thermal runaway, wherever your IC, that is whenever the transistor is running, that means it is provided the supply, it will have the I square R loss. So that increases the temperature. If temperature increases, ICBO, that is your leakage current increases. If ICBO increases, ICEO increases. ICBO and ICEO are related. So if ICBO increases, ICEO increases. Again ICEO is related with the IC because it is one of the parameter in the equation of the IC, as we have discussed earlier. So IC increases, temperature increases. Again this process repeated. So there is no point that fixed bias can stop anywhere this process. So it does not stop the thermal runaway. That is the one point. That's why it is not used. As well as if you change the device parameter, that means if your beta is changed, again IC will be changed. Now what will happen if IC changes? As I have explained earlier, on the load line, if your IC shifts upward because it is increasing, so if it shifts upward, then it will go to the near to the saturation. And if it is going to the saturation, what will happen? As we have understood earlier, that it will cut out the portion which is upper half cycle of your output. Now the next biasing circuit which we want to cover is, that is collector to base bias circuit. Now if you observe this circuit, so what is different from the fixed bias circuit? In fixed bias circuit, we have that resistor RB directly connected to VCC. Over here, first VCC is connected to RC, and after RC there is one branch is taken, and then RB is connected to the through the base. So now collector to base, so it is a kind of thing that is providing you can say one resistor which is from collector to base. That's why the circuit name is collector to base bias circuit. So in this circuit also we will analyze as we have done in the previous analysis. So what we will do, we will write the input side loop equation and we will derive IB. So writing the input side loop equation, first of all we have to consider from here battery. So VCC, then we have to consider the drop across RC. Now what is the current which is flowing through RC? So there is two currents, IC plus IB. Because the current flowing through resistor RB, we will say it is IB. Current flowing through collector is IC. So at this point, at this resistor, what we will have is IC plus IB. So now we will write the equation. So first of all VCC, then the drop across RC. Then if we are considering the input side, then we will have the IB/RB drop, and then we will have VB, and then it is grounded. So let us write the equation. So first of all, VCC is equals to this current IC plus IB into RC plus this current IB into RB plus VBE and then grounded. Okay, so your loop completed over here. Now taking IB common from this terms, Okay, so we have two terms which is containing the IB. So RC plus RB into IB, RC into IC as it is, plus VBE. Making the equation of IB from this, we will write VCC is equals to IB is equals to VCC minus ICRC minus VBE divided by RC plus RB. Now if we know IB, definitely we can find out IC, because IC is equals to beta IB as we know. Okay, so this is from the input side. Now from the output side, VCE is equals to VCC minus, see output side what it contains, VCC, then this drop RC that is having the current IC plus IB, then we will have that drop VCE, and then it is grounded. So what we will write, VCC is equals to IC plus IB into RC plus VCE. So making the equation of VCE from this, we can write VCE is equals to VCC minus IC plus RB into RC. Now if we neglect IB compared to the IC, because IB value will be very very small compared to the IC, so we will write VC is equals to VCC minus ICRC. So now if we know, you can say IB, then we can calculate VCE, and then we can calculate from the output side VCE from the equation. So this is the equation of IB that we have written, that VCC minus ICRB minus VBE divided by RC plus RB. Now VCE is equals to VCC minus ICRC. So over here the term VCC minus ICRC is there, so we will be replacing that term with the VCE. So now our equation of the IB can also be written as VCE minus VBE divided by RC plus RB. Now we have to see that how this collector to base bias circuit that will control the thermal runaway. Okay, already we know that. Okay, thermal runaway, what is thermal runaway? As we know that temperature increases, that increases ICBO, that increases ICEO, then again IC increases, again the temperature increases. Okay, now how this current that will limit your you can say the temperature, or you can say how it will decrement your you can say your temperature, or you can say your IC. Okay, so what will happen? So the temperature increases, that increases your collector current IC. As the collector current IC will increase, the voltage VCE will decrease. Now how it will decrease? Okay, so VCE that reduces, because we know that as IC increases, IC and IB are related. So what will happen if your IB has to increase, then VB is constant. So we are saying that if VC decreases, then so collector current IC, that is IC is equals to beta IB into ICEO. So if temperature increases, your ICEO will increase. If ICEO increases, IC will increase. If IC increases, what will happen according to the equation on the output side loop? It is VCE is equals to VCC minus ICRC. So if IC increases, all other quantities are assumed to be constant. So if this increases, what will happen? VC will go down. Now if VCE goes down, according to this equation, if VCE is going down, so what will happen? The IB will go down. If IB goes down, then what will happen? IC will go down. Okay, so it is like this way. Okay, sorry. So IC will go down. Okay, so this is IB go down, then IC go down. So VC has gone down, so IB will go down, and then IC will go down. So ultimately, due to temperature, IC was increased. Due to that, ICEO was increased. ICEO has incremented the IC. If IC has increased, ICEO has increased. But if IC increases, VC goes down. If VC goes down, then IB will go down. IC is equals to beta IB. So again, IB will go down. So IB will go down, then IC goes down. So this increment in the temperature due to this process has been maintained by this decrement in the IC. So this is stopping the thermal runaway. So this circuit has tendency to stop the thermal runaway. Also, the device parameter variation also can be stopped by this, because IC is equals to beta IB. If IC has been incremented, again due to the decrement in the VC and IB, again IC will be decremented. So this circuit fulfills our purpose of, you can say, stopping the thermal runaway. So this is the circuit of the collector to base bias circuit. So collector to base bias circuits is not used, okay, because it is providing the feedback. Now what is feedback? That is a new term for you. So what is a feedback in electronics? Normal term we understand the feedback, that is whenever we are giving something back to the input, that is called feedback. Over here that resistor RB, okay, that provides the feedback, and whenever in electronics we have the feedback, it will reduce the gain of the circuit. What is the gain of the circuit? Output divided by the input. And what we want in the amplifier? We want to have good amount of the gain. So over here, if I show you the circuit, where we were. So the circuit collector to base bias circuit. So collector to base bias circuit has the feedback resistor. Okay, so let me show you that feedback resistor. So this resistor RB, it is taking some portion of the output and it is giving back to the input. So it reduces the gain of the circuit. So that's why this circuit is not preferred due to the feedback, and feedback is reduces the gain of the amplifier. So this is not desirable. So this circuit is not used. Now numerical. So if someone gives you the circuit like this, it may not be written that it is this kind of circuit, but let's say this is the circuit given to you. Now if you want to find Q point for this, okay, or someone says that find out the emitter current. So first of all, for finding the Q point you need to find IC and VCE, and suppose that's it, in this example it has been told that find emitter current. So emitter current is IE, so IC is equals to IE almost. Okay, so we can say that whatever IC value, that will be your IE value. So now to find the input emitter current, we have to find the IC. So find IC, how to find IC? As we have discussed earlier, we have to find IB first. So you have to write the input side loop equation. So writing the input side loop equation, or directly if you remember the equation which we have analyzed right now, so you can write definitely the input side loop equation. So what you can do is you can write the input side loop equation. So in this circuit, it is battery value is 10. So 10 is equals to 500 into bracket IB plus IC plus 500 kilo ohm. See, value of this is in kilo ohm, this is only ohm. So 500 kilo ohm into IB plus VBE. So keeping that, we can neglect the VBE value. Over here it has been neglected. So VCC minus VBE की जगह only VCC लिखा है इधर. So IB is equals to VCC divided by RB plus beta into RC. Now how this beta has come? IC has been replaced by beta into IB. So we have replaced that over here. So that equation, if we keep these values, we will be finding IB is equals to 18 microampere. Then IE or IC equals to beta IB. So keeping this value of 18 microampere and beta value 100 is given in the circuit. So 1.8 milliampere is your IE value. Now VCE, that is equals to VCC minus ICRC. So VCC is 10 volt as we have seen the circuit, minus 1.8 into RC value, which is 500. So if you will be calculating, it will be coming as 9.1 volt. Okay, so this is how you can calculate the numerical, which is if it is asked. Okay, another circuit which we will cover, that is the bias circuit with the emitter resistor. Now this circuit is kind of circuit which we have seen earlier in the fixed bias circuit. So fixed bias was containing this resistor, this kind of battery, but this emitter was directly grounded. Now over here you have that resistor which is connected with the emitter. So RE resistor is there. So that is different compared to the fixed bias circuit. So let us analyze this circuit for the Q point first. So input side loop, what we will have in the input side loop, we will have VCC, then we will have RB, then we will have VBE, then we will have drop across the resistor RE. So writing the equation on the input side loop, okay, what we will do is we will write the input side loop equation. So VCC is equals to the next drop RB into IB, okay, then V plus VBE, okay, plus VBE, this is the drop between base and emitter. Then we will have IE into RE, then we will have IE into RE drop. So VCC is equals to, we have written the equation, RB into IB plus VB plus IE into RE. So from this, okay, we can make the equation of IB as VCC minus IERE minus VBE divided by RB. So if we neglect the value of the VBE, since it is very small, 0.7 volt for the silicon transistor, 0.3 for the germanium transistor, so you can say IB is equals to VCC minus IERE divided by RB. So this is on the input side loop equation. Okay. Okay, now how this circuit will you can say stop your thermal runaway, that we will see, but let us go to the output side loop first. So in the output side loop, okay, what we have the VCC, then this resistor RC which is having the current IC, then we have drop VCE over here, and then we will have the drop across the IC. So your loop will be going like this. My pointer is not working properly, but it will be like VCC, then you will have RC, then you will have drop VCE, and then you will have drop RE, like that. Okay, so it will be going in that fashion. So writing the equation on that side, what we will have is VCC is equals to ICRC plus VCE plus IE into RE. So that equation we will follow. So VCC is equals to what we have is VCC is equals to ICRC plus VCE plus IERE. So from this we will make the equation of VCE is equals to VCC minus RC plus RE into IC. So this is the equation of VCE. Okay. Now this analysis that is done for, you can say, input loop. So input loop, we are making the equation of IB now. Okay, so coming back to the input loop equation which we have written earlier, that is IB equals to VCC minus IERE divided by RB. Okay, so now this equation is written like this. IE is replaced by the quantity IB into beta plus 1 over here. So now VCC is equals to IBRB plus VB plus beta plus 1 IB into RE. So all these terms are containing only one current, that is IB. So IB is equals to VCC minus VB divided by RB into beta plus 1 RE. Why beta plus 1 RE has come? Because this is beta plus 1, okay, and this is the resistor RE. So that term will multiplication with that RB. Okay, so now if we neglect the VB, then we will have IB equation, that is equals to VCC divided by RB plus beta RE. Now what we have to find is Q point. Q point is IC is equals to beta IB. So whatever equation of IB we have found out, that will be kept over here, and we will get the equation of IC like this. Okay, so this is how you can find the Q point. Okay, now let us come to this thermal runaway, how this circuit can stop the thermal runaway. Okay, so thermal runaway, as we have understood earlier, as the temperature increases, ICBO increases, ICEO increases, again IC increases. Now how this circuit will stop this thermal runaway? So the main point over here, that is the resistor RE. Okay, so because the temperature increases, the leakage current increases. This increases the collector current. Okay, that is your temperature increases, ICEO increases, ICEO increases, IC increases. Now this IC increases, that will also increase the emitter current. Collector current के साथ साथ emitter current भी बढ़ेगा, because IC is almost equals to you can say IE. IC is almost equals to IE. Now if collector current increases, as we understand that voltage drop across the resistor RE will increase, because the drop across RE is nothing but IE into RE. So the drop across the RE, that will increase. Now what will happen if the drop across the RC increases? Then according to the equation, as we have seen, if IE, that is the drop across that resistor RE increases, then what will happen? If this has increased, then IB will go down. If IB goes down, IC is equals to beta IB. So what will happen to IC? IC will go down. Okay, so this is the sequence. As IC increases, what will happen? Your RE will increase, drop across the RE, that means IE increases, IC increases, so IE increases, so IERE increases, so IB will go down because it has the term minus IE into RE. So IB will go down, then again IC will be going down. So this is how it has compensated the Q point. Okay, but that means your thermal runaway, it has stopped somewhere, so it will not increase your IC and your Q point will be stable. Your Q point will be stable. Again, let me remind you that this lecture is recorded for the first year IT students of A.D. Patel Institute of Technology, New Vallabh Vidyanagar, for the subject of basic electronics. So this is how you can say your circuit will protect the thermal runaway. Now let's see one numerical based on this circuit. So numerical is very simple, as we know that just we are given the values, we have found out the equation, so we have to just keep the values. So suppose let's say you are given to find all these three currents, IB, IC and IE. So what you need to do is just you need to apply the equation from the given values and just we need to keep it over here. So this is very simple, just you keep these values, you will get the answer. So this is very simple numerical that you can try it yourself. Okay, I already provided the book to you. Okay, so this circuit numericals are given, we are not going into the details. Suppose you are told to find the Q point, then also you will be able to do it, because we have already seen the procedure. First of all we have to find IB, then we have to find IC, and then we have to calculate you can say the Q point. Okay, now this circuit is also not preferred. Okay, this circuit is also not preferred. That is why it is not preferred. Suppose you are using this circuit, then what will be there is there will be feedback. Okay, that is you can say if you are using that resistor IE, then it will be providing the feedback and that will reduce the gain. Okay, so this circuit is not used for that purpose. So let me show you that this RE is providing the feedback in output side to input side, so that's why this is not preferred. So this is the bias circuit with the emitter resistor. So this is the three circuits which we have seen: fixed bias, then we have seen you can say that collector to base bias, and bias circuit with the emitter resistor. Kindly refer the videos and read the material, and again if you have queries then you can text me. Already I have I've given my number to all of you. So have a good luck, see this, and if you have any query, revert back to me. Okay, let's stop here. Thank you all of you.